All right, Dr. P here, and in this lecture we're going to take a look at multi-step synthesis. I'll actually start with making changes in the carbon skeletons of molecules. So we'll call it carbon skeleton transformations. And the one thing to note is that forming CC bonds is a goal of synthetic organic chemists everywhere. In order to build up a more complex molecule from smaller molecules, you need to be able to form carbon-carbon bonds. So, what reactions have we seen that will do this? Okay, well, we've seen, we could have, let's say, RCH2 X and treat that with Cn minus, so NaCN, something like that. DMSO, acetone, whatever. Do an SN2 and get RCH2C triple bond N. This would work with secondary. Now I'm making a new carbon-carbon bond via an SN2 reaction, but I also have this nitrogen here. Maybe you want to add a nitrogen, maybe you don't. Let's see, what else? We've seen, let's do RC triple bond C minus Na plus, and we'll treat that with R prime CH2Br, and we'll get R C triple bond C CH2 R prime. So if R prime here is actually just a hydrogen, we'll have CH3Br methyl bromide, and we'll be sticking a methyl group on one end. We could use a larger primary alkyl halide as well. Again, this is an SN2 reaction, only we're using the acetylide ion. Now we can use also, we can do RMGX, usually it's RMGBr, and we'll go ahead and treat that with R prime CH2Br, and we'll get R CH2 R prime. So we're going to use our Grignard and react it with an alkyl halide, a primary alkyl halide, and make a longer alkane. Now we can do other things with the Grignard as well. So I could do RMG, I'm just going to say MGBr because it's easy to brominate something, a little bit easier to brominate something than to chlorinate something usually, because we can do the radical bromination. And then we can treat that with magnesium, that alkyl halide with magnesium to make the Grignard, and then go from there. So I can react this with R prime C double bond O R double prime, and then H3O plus. This is actually the Grignard reaction, or what's called the Grignard reaction. Victor Grignard originally, I think, was working on these types of reactions, but then he discovered this reaction as well. So what happens is the R-Mg bond is polar, but the electron density is on, the partial negative charge is on the R, so it functions like a carbanion, and it will attack the electron deficient carbon here. And I'll talk more about this Grignard reaction, this version of the Grignard reaction, in the chapter 17 lectures on alcohols. But what we'll end up with is R, C, R prime, R double prime, OH. Grignard adds here, the MgBr falls off, these electrons go up, we get an O minus, and then the H3O plus in the second step protonates, and we end up with an alcohol. Now, if R prime and R double prime are both hydrogens, we'll make an alcohol that is 1 carbon longer. If we wanted to, we could do our RMgBr and react it with ethylene oxide, excuse me, in ether. Oh yeah, I should mention this is done in ether. That's our solvent. We'll talk about that later in the chapter 17 lecture videos. And then we'll go ahead and protonate, and we will get R, CH2, CH2OH. So using a ketone is a good way to get a tertiary alcohol. So the carbon that has the OH has 3 alkyl groups attached to it. If we used an aldehyde here, we'd get a secondary alcohol. If we used formaldehyde, so H and H, we would get a primary alcohol longer by 1 carbon. With ethylene oxide, we get a primary alcohol longer by 2 carbons. You could use a substituted epoxide, have a methyl group here or something, in which case you could get a secondary alcohol longer than 2 carbons. This is such a good nucleophile, it will attack at the less hindered carbon. Okay, now we do have can remove carbons too. And this is done via oxidative cleavage of C double bond C or C triple bond C. Usually we don't want to be removing carbons because we're trying to build up a molecule, but sometimes we do. So it's just something that was worth mentioning. Okay, so let's take a look here at how we would go about planning a more complex synthesis. Make sure you guys can see all of that. All right, so let's move on here to planning a complex synthesis. I'll put that in quotation marks. Now, before we looked at, the changes made, so we'll want to do that again. So look at how the carbon skeleton has changed, and then also look at how functional groups have changed. We also want to consider regiochemistry and stereochemistry. So as an example, we could, let's say, propose a synthesis for the following. So the typical problem would be propose a synthesis to accomplish the following transformation. Okay, and if we're going to analyze this, let's take a look. First thing, look at the carbon skeleton. I have 1, 2, 3, 4, 5, 6, 7 carbons. Here I have 1, 2, 3, 4, 5, 6, 7, 8 carbons. So I know I'm going to have to create a new carbon-carbon bond. Now what else? I have an alkyne, and here I have a dibromide. So I can start visualizing in my mind some plans. All right, I need to make a new carbon-carbon bond. Oh, I have an alkyne. I can probably add a use an alkynide, or sorry, an acetylide, not an alkynide, an acetylide ion. Turn this into an acetylide ion, and then add a methyl bromide, and that will add a methyl group. And then if I can turn this guy into the right alkene, I know I can add 2 bromines across an alkene. So we'll go ahead and we'll take a look at that in just a bit. Actually, we can do it now. Let me just check and see. I had another example which we'll go over. Let me just check here. So I'm going to let you guys actually take a look at this. So write this down, and you can go ahead and start looking at this based on what I'm going to go over shortly. So to plan a synthesis can work forwards or work backwards. And that's called retrosynthesis. And I've talked a little bit about this in lab. Actually, I think I did a short lecture video as well. So let's take a look at retrosynthesis, or sometimes called retrosynthetic analysis. All right, so the best way to talk about retrosynthetic analysis is just to do it and show you guys what I'm talking about. So let's say we had the following synthesis. So our retrosynthesis would start with working backwards and thinking, how can we make an alkyne? First things first, let's analyze this here. 1, 2, 3, 4, 5, 6 carbons, so 6 C's, and it's an alcohol. 1, 2, 3, 4, 5, 6. 6 C's and an alkyne. So we don't have to change the functional, or sorry, the carbon skeleton, we just have to change the functional group. So we can think of, and really, like, you know, let's do it this way. Let's do our synthesis would be something like, and we're going to go to something else, which is turned into something else, which is turned into something else, which is then turned into, and what we're going to do is, in the retrosynthesis, focus on this last step. So we'll focus on that last step first in our retrosynthesis. So let's take a look at, so our question is, how do we make an alkyne? So if we were going to do our retrosynthesis, typically we'd write out a retrosynthetic arrow, and before we do that, however, look at ways to make an alkyne. And if this is my alkyne, how can I make it? Well, these all the ways that we've seen involve elimination from a dibromide. Okay, because the only reactions we've seen that make an alkyne involve elimination. So, elimination via, we're saying elimination of a dibromide. Okay. And you want to make sure that we're dealing with the right regiochemistry and stereochemistry, or more properly regioselectivity and stereoselectivity, because certain reactions only give certain products. Remember, we can have Markovnikov, anti-Markovnikov, Zaitsev versus Hoffman. Now, I'm going to choose this guy. We're going to use a let me just see here what I want to say. Yeah, I'm going to choose this guy. Why that one? Well, we know how to do it. Okay? We know how to make a vicinal dihalide from an alkene. All right? So you have to think about possible ways to make a product in a given step, and then which starting material you actually know how to turn into that product. So if I'm going to look at my retrosynthetic analysis, I'd go ahead and draw it as follows. I use a block arrow. So this is my retrosynthesis here. A retrosynthetic arrow. And I know, or I'm thinking, this guy is going to come from this guy. Now, I'm not writing down what reactants I would use, what reagents I would use. But remember, when I do the reaction, I'm trying to go from here to here. So when I'm thinking of what starting material gives me that. And so this is what I came up with. Now, let's go ahead and take a look at, let me just add here so far. Let me go ahead and look at the next step. So we'll look at how to make that dihalide. Okay, so what do we have? We can use an alkene to make that, right? We know we have that reaction. So we can go ahead then, and now our retrosynthesis so far is going to be, we make the alkyne from the dibromide, and we make the dibromide from the alkene. Now we'll look at how to make alkene. And in the alkene, let's see here. How can we make an alkene? Well, typically we make an alkene via elimination. So we could use tosylate. We could use bromide, and we want to have the leaving group here so that we make sure we get this guy. All right. If our leaving group was here, we'd have to use a hindered base, which we could use, I suppose. But it's easier if it's on there. Now, let's go back and take a look at, remember, our beginning here, we had an OH. So it's easy to go from an OH to a tosylate. We could also go from an OH to a bromine because we have ways of doing that as well. So I'll show you both of them. So actually, either of these guys is going to, either of these guys is going to work. So we'll take a look at how that will work. So let's go ahead and, sorry, I'm just adjusting, make sure I'm got the page here. So let's look at our retrosynthesis so far. Now you're not actually going to, let me back up for a sec. You should write out a retrosynthesis if it's needed. And usually for multi-step syntheses, you do need to write a retrosynthesis to keep track of things. And it can get you some partial credit too. If you have a legitimate retrosynthesis, but you mess up on the synthesis, I'm still going to see that you knew what to do, you just got details wrong, so that would be probably a 2 for the outcome score. So let's look at our retrosynthesis so far. You're probably going to do this not, when you write it out, it wouldn't be one step at a time like we did here. You'd end up writing it all out. Now, can we make a tosylate or a bromine from the alcohol? the answer is yes. So I could add in a final retrosynthesis step here, and that is my initial starting material there. So now I'll go ahead and write out the synthesis. And this gets written out forwards, all right? So we're going to start here. We're going to go boom, 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 boom. So I'll go ahead and start with guy there. So let's make the tosylate, OTS, or I could make that guy there, and then either of these I can then react to get my alkene, which then I can react to get my dibromide, and then that will react to get my alkyne. Now let's add in our reagents. Okay, we can use tosyl chloride. I'm not going to bother to write in the solvent. Sometimes you need to, but you know, for here we'll make it simpler and not add that. You know, I think Ms. Gibson's list of reactions doesn't have the solvents listed for a lot of them. Okay, we could use PBr3 to make the bromide. And then here, let's just use NaOH or NaOMe, something like that. And now we'll use Br2, typically methylene chloride as the solvent, but you can just write Br2. And then we'll use excess NaNH2 followed by water, and that will do our elimination. I think I wrote that you need to use some heat, so we'll add that in there. So this is our forward synthesis after we've looked at the retrosynthesis. So typically on a problem, and I'll do this when I go through it on the, when I write up the answer key for the practice exam, I'll go through and I'll start writing this. Okay, I know I can make this from this, I can make this from that, I can make that from those, I can make those from this. And then I write it out forward and I'll add in my reagents. Okay, if I wanted to, I could write this as one step here, and so you know I could write this as 1 TSCl, 2 NaOH, 3 Br2, 4 NaNH2 and heat, and then 5 H2O. Whoops. And that gives me my product here. So you could write it out like this. I like to write it this way just because it shows the product of each of the individual reactions. All right, so again, synthesis is putting together a string of individual reactions to get from a starting material to a product, compared to mechanisms where you have a series of steps of bond formation and breaking to get from the reactant to the product. And so you'll have intermediates in the middle, whereas here, with our synthetic steps, we have an actual product of a reaction. All right, so go ahead and take a look, or take some time now to look at this guy here. Okay, so let me write this down again. So let's look at this here. So another example. All right, so this was our other example that I told you about. So go ahead, pause, and take some time to work on this, and then when you come back, we'll go ahead and I'll show you how I would go about solving this one. All right. So I will let you guys do that, and I'm going to put this page back. So let's look at this now. Now, do I have a way to make a dibromide here? Yes, I do. Okay, but, oopsie, what's the problem here? My dibromide, it looks like these bromines are on the same side. So actually, I want to rewrite this because remember, our bromination reaction is anti. So I'm going to want to rewrite this as where I've rotated my bromine around so it's now behind. All right, so if my bromine's behind, my H is in the front, and this guy's on the other side. So really, I've just rotated this around to bring the hydrogen up. Bromine goes in the back, and this guy comes over to the other side. So that means I came from that. All right, I came from the trans. Because if I had the cis alkene and I brominated it, I wouldn't get the two bromines like this, both wedges. Okay, I'd get a wedge and a dash. All right, so let's go ahead then and take a look at how I would make this. Well, how can I make an alkene? I can make it by elimination. How else can I make an alkene? I can make an alkene by from an alkyne. So why don't I try that? Why am I doing that instead of elimination? Well, I'm starting with an alkyne. So in a way, I'm thinking forwards a little bit because I'm thinking, all right, I know I have to use this at some point. So what if I did that? That works, right? I can use sodium in liquid ammonia to do the metal reduction there, and the dissolved metal reduction, and get my trans alkene. And you know, I'm leaning towards this instead of some kind of elimination because it ensures that I've got the right stereochemistry. So again, I'm thinking of my stereochemistry here. Now I know this guy could actually come from my starting material. Okay, now again, when we go back and look at, when we looked at the analysis here, we've added a carbon and gone from an alkyne to a dihalide. So we have to do both of those. Now why didn't I try to add the carbon at the end? Well, I didn't have a reaction that would make just stick a CH3 on something with the bromines. So I thought about how do I know to make this, or rather this guy here. They're the same thing. I'll write equals here. Equals. Well, I can do it from the alkene. Oh, I can make an alkene from an alkyne, and I can make a carbon-carbon bond from an alkyne. So I know how to do that. All right, so that's the retrosynthesis. And now the forward synthesis, which you'd want to write down, I'm going to start with my starting material here and try to draw it. Try to draw your alkynes in a reasonable way that, I don't really like the bent alkynes. I know I said those were okay, but anyway, and so I'll want to go to boom, boom, 1, 2, 3, methyl group, and then that guy I'm going to turn into boom, boom, my trans, and then that guy I'm going to turn into boom, boom, Br, Br. All right. Now, let's take a look here. All right, so what reagents do I need? Well, here I'm going to use NaNH2 to deprotonate, to make my acetylide, and then CH3Br. So I'll get my alkylation there. And then I'm going to use Na in liquid ammonia to do my dissolving metal reduction, and then I'll add Br2. Now, one thing to note is that I actually get the enantiomer here because the Br2 could add from either side. So that's one thing. Sometimes you're going to end up with an enantiomer. And if, you know, I might write here, so plus En for plus the enantiomer, because we do have, you know, chiral carbons there. And if you just need one particular enantiomer, that can be trickier. Okay, so I've got my stereochemistry right, but, you know, because this guy, when we rotate it, equals that guy. But I'm also going to make the enantiomer as well. So it's just something to, you know, to consider. All right, sometimes you can't get around having to make the enantiomer. Okay, so there are some things that you can do to help with this. When you're working on practice problems, go ahead and make a list of reactions you know, or use the lists that I've posted on Canvas. Okay, we have the list of alkene reactions, the list of alkyne reactions, Ms. Gibson's overall list. In the Chapter 17 lectures, I'll go over some reactions of alcohols, ways of oxidizing alcohols, reducing carbonyls to make alcohols, etc. You can also practice synthesis by making your own problems. And so, you know, you could make your own problem and, you know, you could go forwards and then you'll have the starting material and your final product. So just do a few reactions and then give that to your friend. Give them the product and the starting material and the product, but not the intermediate reactions. And so you could do that. You could exchange problems. And, you know, that might be a fun classroom activity to do. Anyway, so that is synthesis, and I know it was a little bit long lecture-wise, but hopefully you stuck with it, and it makes some sense. And yeah, we will go from there. All right, so until next time, stay safe.